All right, so what I would like to show you in this lecture of Math 676 is how to apply the template techniques in C++ that we've talked about in the last lecture to the finite element computations that we've been dealing with here. So we call this thing a dimension-independent programming style because we like to write our programs in deal.II in such a way that they're really independent of the dimension. In other words, that we can compile this program in 2D or in 3D, however we want, but that we have to write it only once. And of course, there's an enormous benefit to this because finite element programs are very large. I mean, they have tens of thousands, hundreds of thousands of lines of code, and if we can write it only once and test it only once, we're certainly twice as well off as if we had to write everything twice for the 2D and for the 3D case, and maybe for the 1D case as well, although that is not quite as important. So what I would like to do is I would like to show you how you build a code that runs in 2D and in 3D and solves the Laplace equation. And that, of course, is step 4. So step 4 is, for all practical purposes, exactly the same as step 3. It almost looks exactly the same, with the exception of the fact that we use templates, where previously we just said triangulation 2 or DOF handler 2 or FE2, these sort of things. So now we use everything in a dimension-independent way. You find it in exactly the same place. You go into step 4. You call CMake as you always did. You call make run, and then we can visualize it in 2D and in 3D, and I'll show you that too. But by and large, as I say, it is almost exactly the same as step 3. So let me walk you through this program. So when you go to deal.II.org, and in the usual place you find your tutorial programs, you click on step 4. You come out with this program here, and it gives you a little bit of an introduction. It talks about the templates that we talked about in the last class. Let me skip all this and just jump right into the program. So in particular, what I would like you to look at is the declaration of the step 4 class. So you remember that before so when we looked at step 3, for example, it had a constructor, step 3, and it had a member function run, and then it had 5 member functions: make grid, setup system, assemble system, solve, and output results that would do the individual parts of this of what this class does. And then it had 6 or 7 member variables, and step 4 looks exactly the same, with exactly one difference, namely wherever we set before triangulation 2, FAQ 2, DOF handler 2, we now say triangulation dim, FAQ dim, DOF handler dim. And what is dim? Well, dim is the template argument of this class. So I should be precise, it's not a class. It's a template. Or in the C++ standard terminology, it is a class template. What this means is that it's a way how I can generate a class out of this template if somebody told me what dim was. Okay? So if somebody told me what dim was, for example, if dim equals 2, then the compiler knows how to create a class out of this template by replacing dim by 2 everywhere in these member variables and in the member functions. Okay? So every one of these member functions will have to be created out of a template where we replace all occurrences of dim by 2 or by 3 or whatever the argument is that was given to the class. So where does this happen? Well, let us look at the main function. So in main, what we do here is we create an object of type step 4 angle bracket 2. So this is the place where we tell the compiler, hey, you've seen this class template. Now replace all of the occurrences of dim by 2 and create a concrete class, an instantiation of this template class that has dim replaced by 2, and then produce an object out of this concrete class that we will call Laplace problem 2D. And then in the next line, please call the member function that you have created out of the template member function run. So the template member function run, this is this one here. So again, this is the syntax to describe a member function of a class template. Okay, so the class template depends on the argument dim, and it has a member function run. And this is what it does. So it outputs the dimension in which we're running, and then it calls the same 5 functions that we've had before. Okay, so what we do here, down here, is we create an object where it replaces dim by 2, and then we call the member function run, where we have replaced dim by 2. In this function we call makeGrid, which of course is again a member function of this class template, so it will call the function makeGrid where it replaces dim by 2. Then it will call setUpSystem where it replaces dim by 2, and so on and so forth. Okay. It turns out that the body of these member functions is exactly the same as before. So if you look at the makeGrid function, for example, you will barely see any difference between step 2 and step 3. So we call grid generator hypercube on this thing triangulation. Well, triangulation was of data type triangulation dim, right? So if you go up here, triangulation, this member variable here, was of type triangulation dim. Well, triangulation dim is actually not a type. But when we replace dim by 2, triangulation 2 is a type. It's a class, right? It's a class that can be generated out of the general template triangulation dim. So what is happening here then when you instantiate makeGrid for a particular dimension, so for example, if it replaces dim by 2, then triangulation here has data type triangulation 2, and it is going to call grid generator hypercube with a 2-dimensional triangulation, which is going to fill it with one single square. But if you call step 4 this class template with dim equals 3, then it will replace all of the occurrences of dim in this member function here by 3. In that case, triangulation is of data type triangulation angle brackets 3, and it will call hypercube with a 3-dimensional triangulation, and that will fill this object here with a cube, so with a single cell that describes a cube. And then it's going to refine either the square or the cube 4 times, and it's going to output for us how many active cells there are and how many total cells there are. So all of the other classes, or all of the other member functions, look again almost exactly the same. So that when you replace dim by either 2 or by 3, it will produce a member function that looks exactly like the one in step 3, for example. So we do this twice in this program. That the first time we call step 4 with argument 2, that gives us a 2D description of the problem, and we run it. And then, because this is enclosed in curly braces, this object here goes out of scope here. And then we start another block here where we create a 3D object that we run again. So I enclose this in curly braces because I don't want the memory that has been allocated for this 2D problem to be still in use by the time we solve the 3D problem. So there really isn't all that much more to this program. There's a few more things where we talk about boundary conditions and the right-hand side. I'm not going to focus on this here. If you want to, you can look this up yourself in the documentation of this program. Rather, I just want to run this program and see what happens. So I'm going to deal.II examples, step 4. I'm going to call cmake -d deal.II directory equals home Bangerth bin deal.II, and then the sources for this particular project lie in in the current directory. I'm just going to compile this all. I'm going to say make to compile it. So cmake didn't compile it. Cmake just set up the environment. It figured out the properties of the system. It figured out where deal.II is installed, for example. Make compiled it. Make run is going to run it. So it's going to say solving problems in 2 space dimensions, 256 cells. We refined it 4 times, so that means I have 16 by 16 cells in 2D. It gives us 289 degrees of freedom. It took 26 iterations in 2D. And then it's going to run the whole thing again in 3D. And you remember, I wrote the code only once, but it's going to run it in 2D and in 3D. In 3D, I have 16 by 16 by 16 cells. That's 4,096 cells. 4,913 degrees of freedom, and it's going to take 30 CG iterations to converge. And there's one single place in this whole program where I really had to do something different for the 2D and the 3D case. That is in the function that outputs everything into a file so that I can visualize it. That's this function here, output results. And the reason for this is that I don't want to overwrite the 2D solution by the 3D solution. So what I'm going to do is I'm going to create an output file stream, which if dim equals 2, then I get a file name solution 2d.vdk. If dim equals 3, I get solution 3d.vdk. So you see that dim, you can always think of dim as a placeholder. The compiler will replace it by something if I instantiate this template. But that doesn't mean that I can't use it in the code itself in conditions, right? So if the compiler replaces this by 2, for example, then the condition here will simply be 2 equals 2. That is true, and so I get solution -2d.vdk. If it replaces dim by 3, then the condition will be 3 equals 2, which is definitely not true, it's false. And in this question mark colon operator, I will come out in the third branch, and I will get the file name solution -3d.vdk. So if I run this, as I said, I get 2 output files. I will have solution 2d.vtk, and I will have solution 3d.vtk. And let us visualize these. So I'm going to use again visit. So if I look at the 2D solution first, so I'm going to open the 2D solution, then I will add to it, for example, a pseudo-color plot, and it's going to look like this. So if you look at the exact description of what step 4 solves, we have non-zero boundary conditions in this case, and I should show you the solution as a 3D plot. So sorry, I need to add an operator, transforms, elevate, draw. So the solution is going to look like this. And I think I should be able to also add a mesh to this. That fails at first, and the reason is that elevate wants to elevate whatever it's plotting, in this case the mesh or a solution, by the thing it is plotting. So at this point it doesn't really know by what it's supposed to elevate the mesh. Let me go through transformation here. Elevate, and I need to say elevate by scalars by the solution. Okay, apply, draw. Okay, and now I also have the mesh plotted on this surface. So you see that the mesh is, of course, far too coarse to really show the solution very accurately. And as before, I have all sorts of crap in this particular picture. So let me remove all of this and produce a much nicer picture like this, where in the best of cases, I'm willing to concede that we should have a bounding box, but this is the picture that I really want. This shows the solution as I want it to. So as I say, the mesh is not nearly fine enough to really accurately solve this particular problem, but this is how it looks. This is the 2D solution. And so what I would like to show you, of course, is also how the 3D solution looks, that I got out of exactly the same program. So if I remove these again here, and I'm going to open instead the 3D solution, solution 3D. Now, 3D solutions are a little bit more difficult to visualize because I cannot look into a body. So what we typically do is, well, in the first step, we would just plot a pseudo-color, but that's going to just show the solution on the surface of the body, right? And I can look at this, of course, but I can't see what's happening on the inside. So one of the things that we can always do is, instead of showing the pseudo-color plot on the surface, I could, for example, show contour surfaces. So let me show you how this looks here. So I get a plot like this. So you can, if you compare this with how the 2D solution looks, you see that the solution becomes very smooth in the inside of the domain and really most of it is actually happening on the outside. This is a little bit too busy a plot for me. I can reduce the number of levels, let's say, to 6. Then one of the things that you learn relatively quickly is that if you have isocontours in 3D, that you cannot look through them either, but I can make sure that I can by reducing the opacity of each one of these levels here. So a common strategy is to use something that grades the opacity in one direction or another. So let me show you how this looks here. So I come out with something like this. So some of these surfaces, these ones here, for example, are not transparent at all, whereas the red discs here are almost completely transparent. So we can play with these sort of things. So there's a lot of nice pictures that you can make this way by using opacity of isosurfaces. The point I wanted to make with this program is that, as you saw, we really wrote the program only once. And it worked in 2D, and it worked in 3D. And the solution that we compute is, of course, something completely different. In particular, it takes, if you actually timed this, it takes far longer, for example, to compute the program solution in 3D than it takes in 2D. But because I wrote the program only once, there was only one set of lines of code that I need to write. And in particular, there's only one set of lines of code that I need to debug. And one of the things that you learn fairly quickly is that when you write bigger programs, that you spend most of your time with debugging your problems, not with writing the programs. And so it's really helpful if you can debug your problem in 2D, where every computation is fast, rather than having to wait for long amounts of time in 3D, where you might have to wait for several minutes before you finally hit that nasty bug. So for these sort of things, this approach of dimension-independent programming is really useful, where you write the program only once, and then you run it in 2D or in 3D. So the usual approach applies to step 4 as well. The next step for you should be to play with this, right? Load it into an editor, for example, Eclipse, and play with it. Change the boundary conditions, change the geometry. At the bottom of the results section, there is always this subsection where we talk about possible extensions of this program, other things that you could do with it. Follow these recommendations, play with it, and edit around. See what happens when you do this, see what happens when you do that. That gives you sort of a feel of what can be done and what is more difficult to achieve. So with this, I'll stop on step 4, and we'll come back on step 5, which is a program that deals with a sequence of meshes, where you start with one mesh and then you look at the next finer and the next finer and the next finer mesh. Because ultimately, of course, what you're always interested in is not so much solving a particular PDE on one mesh, but what you want to do is you want to solve the PDE. And so you need to ask questions like, well, how close is my solution actually to the real solution of the partial differential equation? And so you want to investigate questions like convergence. How far is my current iterate away from the exact solution? And that is one thing that you can typically do by using a sequence of meshes that becomes finer and finer, and looking at the solution and see it become more and more accurate. And that's what step 5 will be about.